Hi, so this is 3.5 probabilities using combinations. Now, up to this point in chapter 3, we have been doing a lot of combinations work. So we know that combinations is really to deal with situations where order doesn't matter. Okay, now we're going to tie it back to what we've learned previously in chapter 1, which is the basic idea of probability. So, for example, if I, let's say, wanted to figure out, what is the probability of getting heads when I toss a coin, well, I know that this is represented by 1 over 2, right? Where 1, what does 1 represent? Well, that's the number of ways in which heads will happen when I flip a coin. And 2 is number of, I guess, all the possibilities that can happen. So for example, this could be either heads or tails. And so this idea of probability is prevalent in what we will be doing in this 3.5. Okay, so you have to remember that the numerator is the number of your desired outcome, or the number of ways for your desired outcome to happen. And the denominator is kind of like the number of ways of all possibilities. Okay, so please bear that in mind. And so let's go through example 1. It says a manufacturer of calculators would like to separate defective calculators from calculators that are acceptable. Through an error, shipment of 12 calculators is sent out of containing 3 defective, 9 acceptable, and the customer buys 5 of these calculators. Okay, so the first thing I'm going to do, because this is super wordy, I have to write it in point form so that I just for myself, so that I know what is happening. So there's 12 calculators in this shipment. 3 are defective, 9 are acceptable, okay? And the customer buys 5 buys, okay? So the first thing I'm going to do is, in part A, if it's asking what is the probability that all 5 will be acceptable, I am going to first identify what my desired outcome is. Okay, so let A be the event that, well, if all 5 are acceptable, that means, okay, then that's pretty much it. All 5 are acceptable. Okay, so that's pretty straightforward. So if I want to express my probability, I need to figure out or write it so that I have number of desired outcome over all possibilities. Okay, so let's look at the easier part of the two, and that is getting that the all possibilities part. Okay, so we're dealing with, we got 12 calculators, we have 5 that we're going to buy. So without discrimination of what is acceptable or not, I know that 12 calculators, I am picking 5. So that is always going to be my total outcome. Okay, and if I want, let's say, just only 5 acceptable calculators, well, how many acceptable calculators do I have? I have 9. And of those 9, I want all 5 to be acceptable. Okay, you could also if, let's say, for the purpose of doing this question, you want to include, well, if 5 are acceptable, that means you don't want any defective. So really, if you want to include the defects, you can just say 3 choose 0. But we know that 3 choose 0, that always amounts to 1. Okay, so we technically do not have to write that. So I'm going to rewrite this expression. Well, at this point, we're just really using a calculator to determine what these values are. So 9 choose 5, is 126 on the calculator, and 12 choose 5 is 792, which gives me a probability of 0.159. Okay. For these type of questions, it's always a good idea to express your final answer with a decimal value and to round it to 3 decimal places. If you round it to 2, you might have a tendency to like over round. So 3 is always a safe value to, the third decimal place is a safe place to round to. So let's do part B. What is the probability that 2 will be defective and 3 will be acceptable? So right away, I am going to tell my the people reading my work what the desired outcome is. So let B be the event that you have 2 defectives and 3 acceptable. Okay, please write that every time when you are doing these questions. So now I'm looking for the number of ways in which you get 2 defectives and 3 acceptable over all possibilities. So how many defectives do we have? We have 3 defectives, and we're still choosing. We have three defectives, and we're choosing 2 of them. Okay, so that means we are going to do 3 choose 2, and for the acceptable ones, there's 9 acceptables, right? There's 9 of them, so 9 choose 3 over 12 choose 5. I mean, the sample space for all the possibilities would not change because we are still talking about the same situation. So using my calculator, you should be getting 0.318. Okay, so that is example 1. Now, example 2 is very similar. So a basket contains 12 apples. So right away, I'm going to write in point form on the side of my notes what they're trying to give me. So 12 apples. Oh, so 12 reds. And then you have 8 greens. And you're going to select four of them. Okay, so you're going to find a probability of each of the following events. Now, because the space that we have on your notes is not very big, I am going to actually identify my event up here. Okay, so let A, well, what is A? Well, you want 4 apples selected and you want them to be red. So that means let A equal to 4 red apples. Okay, so if I were to do part A, where I'm finding the probability of A, I can figure out the number of desired outcomes I will get, and then put it, and then divide it by the all possibilities, number of all possibilities. So I'm going to do the entire possibility first, just so, because I think that part is easier. So basically, you're picking 4 apples, and how many apples are in that basket? Well, that will be 20 apples, right? Because 12 plus 8 is 20 apples. And so for A, if I'm picking 4 red apples, then that's really, well, that means I'm picking the 4. And how many reds do I have? I have 12 reds. And remember, so do I have to choose any greens? Not really. So you know what? I'm not even going to bother with the green apples at this point. Because, well, okay, fine. You can put 8 choose 0 for the greens, but that really amounts to 1, as we saw in example 1. So this really If you do this using your calculator, it gives me 0.102. In part B, they want all 4 apples to be green. So I'm going to let B equal to 4 greens. Okay, I'm just abbreviating because there's not a lot of room on this piece of paper. So P of B is equal to number of outcomes for B over all possible outcomes. So all possible outcomes immediately, the situation hasn't changed. So it's still 20 choose 4, but for the green apples alone, well, there's 8 of them and I'm picking 4. I don't really care about the reds. It will turn into 1 anyways, as you saw in the part A. And using a calculator, it's pretty much 0.014. Okay, and then part C, I want 3 reds and 1 green. So C is going to be 3 reds, 1 green. Okay, so that means probability of C means I need to take the number of ways I can get C over all possible outcomes. So goes without saying that the sample space will be the same for all possible outcomes, but if I want 3 reds, that means I can, out of the 12, I'm going to pick 3 of them, and of the greens, there's 8, I am going to pick 1. Okay, and so using a calculator once again is 0.363. And finally, part D, of the apple selected, you want more greens than reds, but it assumes that at least there is at least one of each type of apple. Okay, so read that really carefully. Okay, these questions require a lot of reading comprehension and a lot of inferencing skills. So what does that mean? Well, okay, I want more greens than reds. So that means I should have 3 greens and 1 red, right? Should I have 4 greens and 0 reds? Well, that cannot happen because remember, you need one of each apple. So really, this is the only outcome that we are looking for. So the probability to get D then is I have to take the sample space of D divided by all possibilities, and that will give me so 3 green. So 8 choose 3 green apples, and 12 red apples, you're picking one of them. And that gives me 0.139. Okay, so that's example 2. We will move quickly to example 3. Example 3 says a scratch and win contest at a store allows you to scratch 5 numbers. If all your numbers match the winning set of 5 numbers chosen from 1 to 25 without regard for order, you win the grand prize. The question is, what is the probability of winning the grand prize? So let's try that. So we are, first things first, we are going to identify what our event is. So let A be the event of winning grand prize. Okay, so I'm just going to write exactly what the question is telling me. Now, we have to be very careful here. What does it mean to win a grand prize? So if you reread that first paragraph, well, you're basically picking 5 numbers out of numbers 1 to 25, right? And if you match, then that's how you win the grand prize. So in other words, what I really want to know is, or what I want is that all 5 chosen numbers have to match the 5 winning numbers. Okay? So to get probability of A, I need to find the number of desired outcomes that can happen and divide that by all the outcomes. So always I start at the bottom because that's always the easier part. Okay, so if I have numbers 1 to 25, that means I have 25 choices and I am picking 5 numbers. So 25, choose 5 should be at the bottom. Now at the top, we want to make sure that those 5 chosen match the 5 winning. So 5 chosen matches the 5 winning. So in this case, how many choices do I have? Well, the 5 winning numbers, and of the 5 winning numbers, I need to pick 5 of them. Okay, so 5 choose 5 is equal to 1, and the bottom is 53,130. So that's, if you use your calculator, you will get something almost close to a 0. Okay, which makes sense because that's very unlikely to win the grand prizes for any lottery. So, so for an answer like this, where you are writing so many decimal values and it's almost to a point where it's close to 0, it's always probably better to just give me the fractional answer. And that's what I will be looking for. Okay, and so in part B, I will show you how to do that. So let B, okay, so what is B? B is to win the second prize. 4 of the 5 winning numbers must match. What is the probability of winning second prize? Okay, so let B be the event of winning second prize. And let's explicitly identify what that means, that of the 4 winning numbers, of the 5 winning numbers, I have chosen 5, right? So that means at the top, that means I will be choosing 4 winning. And so if 4 of them match, that means there's 1 that doesn't match. So 1 will not win, okay, or not match. So this is going to be P at B, which equals to N at B over N of S. Okay, so the bottom identical because we're talking about the same situation here. But if I want the 4 winning numbers of the 5, that means I have 5 choices of winning numbers. I pick 4 of them. And how many? So if 5 of them were winning, that means how many of them are the losing numbers or the not winning numbers? That would be 20, right? Because of 25 numbers, 5 of them are winning. That means 20 of them are losing. And of the 20 losing numbers, I should have 1 of them. So I am going to use my calculator, and that gives me 100 over 53130, which approximates, it's a little higher than the other answer, but still almost close to 0. So you can pretty much present both answers, the fractional and the decimal. Okay, so next, let's look at example 4. All right, so a university task force of 8 people. So immediately, again, let's write that on the side of my notes. So 8 people is formed from 16 members of student government. So there's 16 students to choose from, and there are 10 professors. So let's write that there. And each person is equally likely to be chosen. What is the probability that there are an equal number of students and professors? Okay, so let's write out what event A is. So let A be the event of equal number of students and professors. So equal number between the two. So that means if remember, I'm choosing 8 people. And so of the 8 people, if I want equal number on both students and professors, that means I want that 4 students, right? 4 students are chosen and 4 profs chosen. Okay, so probability of A is pretty much the number of ways to choose 4 students and 4 professors. And right here, this is the pool in which my selection is happening. So of the students, so 16 are in my pool, I'm picking 4. And I have 10 profs here, and of the 10 profs, I'm picking 4 of them. For my total outcome, I'm picking 8 people, and how many do I get to choose? Well, there's 16 students, 10 profs, so that makes 26 people. Okay, and using a calculator, as I have been encouraging you to use, it is 0.245. Okay, and for part B, what is the probability that at least 6 members are students? Okay, so we have looked at this a lot when we were doing 3.3. Okay, what does at least mean? So we are going to spell that out explicitly. Okay, so when they say at least 6 members are students, we're talking about, well, we can have the case where you have 6 students, right? You can have 7 students, or you can have 8 students. Okay, mind you, we cannot have 9 students because 8 is the maximum number of people that can be on this committee. Okay, now you also have to remember, well, this is the direct method. And if, let's say, I want to evaluate it using indirect, well, you can also look at it this way, where it's not 0, not 1, all the way to not 5. But using the indirect method means I would have to go through like 6 different cases, right? Because 0, 1, 2, 3, 4, 5, that's a lot of work to do. So you know what? I am actually going to go with the direct method, because here I just have to look at 3 individual cases. Now, when you are looking at 6 students, 7 students, or 8 students, it kind of implicitly implies something about the professors, right? Because if there's 8 people chosen and you have 6 students, that means you will have 2 profs if there's 6 students. If there's 7 students, there's 1 prof. And if there's 8 students, there's 0 profs. Okay, so the blue represents profs. So having that spelled out very clearly to what we are looking for, now we can tell people what we want. So let B be the event that 6 students, 2 profs are chosen, or 7 students, 1 prof, or 8 students, 0 profs are chosen. Okay, so please make that very clear to you before you start calculating. You have to be able to identify what is your desired outcome. And so this is my total outcomes at the bottom. At the top, I am going to go through each case. So remember, we have the 6, the 7, and the 8. Okay, so we're going to write the situation for each of them. So I want 6 students, so 16 choose 6, and then the 10 profs I choose 2. Okay, plus 16 choose 7 times 10 choose 1 plus 16 choose 8 and 10 choose 0. All right, so after doing all that work and hopefully with an awesome calculator, you will realize and come to the conclusion that it's 0.312 as your final outcome for part B. And to answer part C, which outcome is more likely to occur, you can say that B is more likely to occur just because when we were looking at, the two numbers that we came up with at the end, B has the higher value. Okay, and finally, I want to walk you through example 5, applying Pascal's triangle to probability. Now, we talked about it briefly in another class, but I can walk you through it again. So in the game of Plinko, a disc is dropped into a slot at the top of the board, so it has to start from here, okay? So this is where it starts. When it hits a peg, it falls to the left or right as it travels down the board. State the probability that the disc ending up in each slot at the bottom of the board. So they're saying they want to know what is the probability that the ball will be dropped in each of these 5 letters. So I'm going to write it on the side of my notes. Well, that really, what am I looking for? P of A, I'm looking at P of B, I'm looking at P of C, P of D, and finally P of E. Okay, so I've identified the 5 things I'm going to look for. Now, let's play this game. So the ball is dropped, okay, it goes down this way, and I know that it can only get to this particular peg. So this peg, there's only one way to get there, okay? Now from this peg, it can either go left or right, so that means it can go this way or this way. And seeing that it has to come from this first peg, right? From this first peg, that means the next 2 pegs, well, there's only one way to get there because it has to come from this one, where there's only one way to get there. Okay, now if I look for the third tier of pegs, 1, 2, 3, well, I know that the ones on the 2 ends, well, these have to be 1 because it comes from the previous pegs, right? There's only one way to get there. But for this middle one, well, the middle can either come from this, the one on the left, or this one, the one on the right. So that means really there are 2 pathways in which this peg can get to this particular point. Okay, and we know that, well, there's a pattern here where the outside, the edge of the triangles, they will always be 1 because each of these have to come from basically that one singular pathway. And so I know that to get to A, there's only one way to get there. And likewise with E, because it's on the far edge of this board, E, there's only one way to get to E. Okay, now the middle stuff, let's work through that. So to get to this particular peg, it has to come from 1 or 2. So that means there's 3 here. And likewise with this, 2 and 1, there's 3 pathways to get there. And to get to B, there's 1, it comes from the first, this peg, which is number 1, and there's 3. So this has to be 4. 3 and 3 coming from these two will give me 6. And 3 and 1 will give me 4. Okay, so really what I can do is, what I've found is that the number of ways in which this ball can be dropped all the way to the bottom, and how many pathways do we have in total? So 1 plus 4 plus 6 plus 4 plus 1, that will give me 16 ways, right? Yes, it would. So now I'm going to write that each of them will have a total outcome of 16. Okay, but the numerators will be filled in by their respective numbers. So A is 1, B is 4, C is 6, D is 4, and E is 1. Okay, now the last thing I'm going to do is, well, I don't really like to present my fractions as 4 over 16 because that's not reduced. Let's reduce that. So 4 over 16 is really 1 over 4. So that's that. And 6 over 16 is 3 over 8. Okay, and so in the end, I have basically stated all the probabilities for each of the different letters at the bottom. Okay, I hope you enjoyed this video, and I'll talk to you next time.